What's up, everyone? This is video number 2 for the geometric definition of a parabola. And in this video, we're going to look at two things. Being able to shift the vertex of our parabola so that it's no longer at the origin. And we'll see how that affects the equation of the parabola. And then we're going to look at some applications to parabolas from this geometric definition. Okay. Now, on your screen here, you see the equations for our parabola in the 4 different scenarios of opening right, left, up, down, and the vertex now being considered at the point HK rather than at the origin. All right. Now, understand that the equation for the parabola changes based off of our transformation rules. Okay. So what I mean by that, let's consider the parabola that's opening to the right here. In the previous video, when we said the vertex was at the origin, the equation for the parabola should follow the format y squared equals 4ax, right? Well, now that the vertex is at the point of hk, all I need to do is subtract h from x. I need to subtract k from y in my equation. Other than that, nothing else changes from the properties associated with the focus, the parabola, and the directrix, okay? So don't try to memorize everything that you see on the screen here. As long as you know how the a value of your equation leads you to your focus, your directrix, and then you know how h and k lead you to your vertex, you're going to be fine, okay? All right, example 4. Graph and find the equation of the parabola whose vertex is at 4, -2, and whose focus is at 6, -2. So the first thing we should, of course, do is plot those points. 4, -2 is right here. 6, -2 is right here. So the focus being to the right of the vertex tells me that my parabola is opening to the right. The distance between those 2 points is 2, so my a value associated with my equation should be 2. And then that's going to lead me to finding my directrix. So from the vertex, go 2 units to the left and draw a vertical line. That's the line whose equation is x equals +2. All right. From here, I'm ready to make my equation. All right. So I need to use the coordinates of the vertex when I make it. So think of 4 as an h value, -2 as a k value. So in the case of the parabola opening to the right, it's the y variable that's being squared. So I'm going to begin with y subtracted by the y coordinate from the vertex. So that's y subtracted by -2 being squared equals, if I'm opening right, I should have a +4 times my a value of 2 being multiplied by the quantity of x minus 4, the x coordinate from the vertex. So cleaning this up, this is y plus 2 to the second power is equal to 8 times the quantity of x minus 4. All right, so there's my equation. And now I can use my coefficient of 8. I know that that's the length of my focal chord, right? So cutting that in half, that's 4. So from the focus, I'm going to move 4 units up. 1, 2, 3, 4 takes me right there to the point 6, 2. And I also move 4 units down, 1, 2, 3, 4 to the point 6, -6. And that'll give me the 2 points for the focal chord so that I can complete the parabola. All right, now let's just verify algebraically that those 2 points are on there. So if I use the x coordinate from my focus, which is 6, plug that into my equation, and then solve for y. So I have y plus 2 squared is equal to 8 times the quantity of 6 minus 4. So 6 minus 4 is, of course, 2. 2 times 8 is 16. Y plus 2 squared equals 16. Square root both sides. Y plus 2 is equal to plus or minus 4. If I subtract 2 over, 4 minus 2 is 2. Negative 4 minus 2 is negative 6. So that leads me to the points of 6, 2, as well as 6, negative 6. Those are, in fact, the 2 points that I plotted to make that focal chord. So again, just proving that those are, in fact, points that satisfy the equation that we came up with. All right. Now, some applications to parabolas. Lots of different applications as they relate to this geometric definition. One such is involving a paraboloid. A paraboloid is going to be a three-dimensional figure. It's a surface formed by rotating a parabola around its axis of symmetry. Okay, so let me illustrate this. All right, so what you see on the screen here, that is a parabola. It's graphed in 2 dimensions, but technically I have a 3-dimensional coordinate space to this illustration. And what I'm going to do is I'm simply going to take the green parabola and I'm going to rotate it around its axis of symmetry, which in this case is the green axis that you see there, okay? So as I rotate around, you'll be able to see a 3-dimensional figure is formed. This is known as a paraboloid. Okay? It's kind of like a dish, right? And there are several applications to paraboloids. So searchlights involve a paraboloid. Notice that where you position the light source itself, that's like the focus related to the parabola that has created the paraboloid making the light. You also have a telescope. It has a paraboloid that helps reflect your images off the paraboloid to help you visualize everything through the telescope. And then the example I want to cover is involving a satellite dish. A satellite dish is shaped like a paraboloid of revolution. The signals that emanate from the satellite, they strike the surface of the dish and are reflected to a single point where the receiver is located. And that would be like the focus associated with the parabola that was used to create the paraboloid of revolution. All right, so let's suppose we have a dish that's 8 feet across at its opening and 3 feet deep at its center. At what position should the receiver be placed? That is, where is the focus of the related parabola? So over on the right, you have a picture of the satellite dish itself, right? 8 feet across, 3 feet deep. What I've done is I've transitioned this into a parabola that's in the coordinate plane. And I made it easy on myself. I put it so that I position it so that the vertex of the parabola is at the origin. All right. And then think about it. If the parabola is, or the dish is 8 feet across and then 3 feet deep, that leads me to 2 points on the parabola. So they would be the points of 4, 3, as well as negative 4, positive 3. All right. Now understand, those 2 points, they aren't for the focal chord. All right. These are just 2 random points on the parabola. Okay. So what I want to do here is find the coordinates for the focus using what I have reasoned out. Okay. Well, the way I've positioned this, I have the parabola opening up with a vertex at the origin. So this parabola follows the equation x squared equals positive 4ay. All right? And ultimately, to know the positioning of the focus, I need to reason out my a value. That tells me I need to be able to plug something in for x and y in this equation. And that's where the points of 4, 3 and negative 4, 3 come into play. Pick one of those 2 points, plug their coordinates in for x and y. So I'm just going to use positive 4 for x and then positive 3 for y. Now I solve for a. So 16 is going to equal 12a. A is going to equal 16 twelfths, which is going to reduce to 4 thirds. All right. So that focus should be at the point of 0, 4 thirds. And for the purpose of this problem, I'm going to say that my receiver should be placed 4 thirds of a foot, or 1 1/3 feet, from the bottom of the dish. Okay. Okay. There we go. That's it.